Yes, we'll need a pan.
Yes?
Good idea. Heat-proof gloves. Useful when you're cooking.
And do I need the sugar?
Yes, please. We'll need the sugar. That'll do.
And this?
And a saucepan. We're going to make scientific toffee. Delicious. Weigh the sugar, put it in the saucepan, and dissolve it in some milk. Another butter, too. And carefully onto the stove with it, and finally, add something else. Heat. Now look what's happening to all those different ingredients now. They've all changed into something quite delicious. Be careful, it's very hot. If you know what things are made of, there are thousands of different materials that people can make. Disc 35, please. I'll switch myself to replay and show you. Under the microscope, granulated sugar crystals look like this. These are crystals of demerara sugar. Here's some caster sugar. And here they are again at even greater magnification. Guess what this is? It's ordinary salt. This crystal is the sort you find in diamonds. And this one is an emerald crystal. Baking soda? Tin? Copper sulfate? Epsom salts. Look at all those different shapes. You know, you can grow some pretty spectacular crystals with things we've got right here in the kitchen. Fill the glass with water.
I'll get these labels.
I'm glad to see you're keeping records, Sylvia. That's what scientists always do. Now, big spoonfuls of washing soda. Dissolve them in the water and stir it all up. We've got to make a liquid solution so strong it just can't dissolve anymore.
They're all gone.
Wet a piece of thick white string and put it in the solution.
These?
That's right. It'll give the crystals something to hang on to as they grow.
Still not very hot.
There you go. Right, now put the label on.
No, wait. It goes right under. Right, that's
Right, I'll put the label on.
Now the label. Washing soda, so we don't forget what's in there. Now for the next lot. Copper sulfate from the pharmacy. It's a lovely blue, isn't it? Same as before, as strong a solution as you can possibly make. And hang the wet string in it. Now I can show you what will be happening in those glasses over the next few days. These are crystals actually growing. I've speeded it all up so you can see how they do it. They're taking the material they need to get bigger from the very strong solutions they're growing in. All sorts of shapes and sizes. That's what crystals look like when they're growing. Isn't that pretty? There are crystals in all sorts of things. Split a pencil open if you can. And do you know what that piece of pencil lead is really made of? It's mostly black carbon crystals. And Mummy's very special diamond? Be careful now. Would you believe that it's made out of the very same carbon crystals as the pencil lead was? But there's a big difference, all right, isn't there, Tom? What do you think made the difference? Disc 41, please, Tom. That'll give you a clue. Over to replay. We are deep down inside a volcano. It's so hot the rock has actually melted and it's boiling and bubbling. Diamonds are created in places like this. The crystals of carbon are squashed under tremendous pressures in fantastic heat until they are absolutely cooked. And that can take years and years. When they've cooled down and a jeweler gets to work on them, those carbon crystals end up looking like this. Very precious and very beautiful. This, as you can see, is cut glass. And though it's hard, not as hard as a diamond, of course, it's not a crystal. It's really a liquid. The things aren't always what they seem when you're investigating materials. Look at that glass tube. Even though it's a kind of liquid, my assistant can snap it like a dried twig. But it's easy to understand it's a liquid when you see it like this. It's a bit like toffee. It's not so easy to see it's a liquid when big slabs of heavy glass are laid out like this. These craftsmen are making a stained glass window, a huge jigsaw of glass shapes, and they're sticking them together with a special glue. This window was made for a cathedral. It'll probably still be there hundreds of years from now. But it won't be the same thickness all the way through. If you ever have the chance to go to a very old church, look carefully at the stained glass windows. You'll find that because glass is really a liquid, over the centuries, the windows have flowed downwards, and that's why an old stained glass window is thicker at the bottom than it is at the top. And sometimes, when they're very old, windows just get tired and they break. Take a wire coat hanger and bend it backwards and forwards for a while. Hard at first, isn't it? But keep going. Something is happening to the molecules inside the wire. Feel it getting hot? And a bit easier to bend now. You're making those molecules do a lot of work. They're starting to jiggle up and down very fast now. That's why the wire is getting hot. In the end, it's all too much for them. Many metals are really quite flexible, but bend anything too much, and the molecules in it just give up. Here's a metal joint that is just in the process of giving up. That grey colour means that it's turning into crystals. It's crystallizing. Here it is under a very high-powered microscope. You can see the crystallized metal, and here's one that's actually broken. Looks as if my assistant is up to something interesting next door. This special machine can measure very accurately what it takes to break the molecules in a material. She's putting in a piece of copper wire and telling the machine to find out how strong it really is. Bit by bit, the wire is being stretched until the molecules just can't hold together anymore. This stuff is really stretchy. It's the material plastic shopping bags you get at the supermarket are made out of, so it's meant to be able to carry very heavy weights. But even the special molecules in this stuff give up when the strain gets too great. Under a special light, these patterns show how the molecules are stretched and squeezed in all directions when they're under strain. A section of railway line, and the molecules are certainly working hard here. And look at this, the stress where two cogwheels mesh. A spanner tightening a nut. The molecules in the spanner are being pushed and pulled in all directions. And the strain round big bolt holes in a metal plate that was used to hold railway lines. That's it. There's a pair of tights in there somewhere, Surya. See how when you stretch them, all the loops that interlock bunch up this way and that way to show you where the stresses are? That's what happens to molecules in materials when they're put under strain. Now, have you got everything ready for the next experiment? Let's find out what happens if you do something to stop the molecules from moving and stretching. An elastic band and a wooden ruler to hold it with, and the sort of cold spray they use in radio repair shops. When you squirt some of the cold spray onto the elastic, it freezes a bit of the band. Now, when you try to stretch it, the frozen molecules just can't move around anymore. They've lost their elasticity. Now, my assistant's going to show what happens when you stop molecules moving around when they're trying to. This is liquid nitrogen. It's so cold, it freezes almost anything it touches. Watch what happens when she puts a piece of stretchy rubber hose into it. In a few seconds it will be colder than it is at the North Pole. And what do you think will happen to that squashy rubber? That's a good idea. Goggles to protect your eyes. She's done this before. The squashy rubber breaks like pottery. A mushroom with its molecules frozen solid. Smashes like glass. Now a rock-hard tomato. With all their molecules frozen stiff and locked tight, the grapes can't bend anymore, so they crack apart like little teacups. Now look at this flower from the garden. Amazing, isn't it? Switching to replay. The leaves on the tree are made from the same type of living cells as a flower. If you could look inside the tree, this is what you'd see. Living cells. But when they die and shrivel up, they become a different sort of material. A fibrous material that is very strong indeed. Here's something that came from a tree. Can you guess what it is? Look at those fibers. They look as if they could be very tough, don't they? Have you guessed? They're all microscope pictures of the fibers in a piece of newspaper. Tear up a newspaper into strips like fibers, and this experiment will show you how strong fibers can be. You've got the balloons and some wallpaper paste. So stick the strips of paper over the balloon, first one way and then the other, crisscrossing each other just like fibers. They call this paper mache. It's a messy old job. While you're doing it, have a look at this. These men are using glass fibres to make a boat. They're pressing the glass fibre matting round a boat-shaped mould. Then they soak it with gluey resin, and when it's dry it comes out just like this, a glass fibre boat. There are lots of them about these days. Right, finished and dry? Now, Tom, all you've got to do is burst the balloon inside. Go on, very good. That's it. The balloon's collapsed, but the papier-mâché fibres haven't.
Like a hot air balloon.
Reminds me more of an egg. Did you know that eggs are extremely strong? My assistant's got an egg in that stretching machine she was using before. Only this time she set it up so that it's a squashing machine instead. Look at the force on that egg. The numbers are spinning round. But in the end, the machine wins. It always does. The strength of things is often to do with their shape. You can take something quite flimsy and simply by changing its shape, you can make it quite strong. Like that banknote you've got, Tom.
Balance on top of that.
I bet I couldn't.
Do you think that little piece of paper is strong enough to hold up a whole kilo jar of lentils? Yes, it is. Not because the paper itself is strong, it's because the shape of it is strong. Tubes are amongst the strongest shapes we know. Thank you, Pierce. More tubes, eh? What are they?
They're from a cow.
That's right. They're pieces of bone.
From a cow.
When you take some of that marrow out, you'll be able to see the tube shape more easily.
Tubes in. It's a bone. So is this. It looks like.
Look, you can see funny veins sort of thing.
That's it.
It's this shape that makes bones so strong. Pop in disc number 64, please. When things have to be really strong, when people's lives depend on it, very often you find that engineers build them out of tubes. Bridges for one. And do you recognize this? Or this? Something that has to be extra strong and safe. Yes. Bicycles are made out of tubes for that very reason. A piece of stiff cardboard and 4 cardboard tubes. Quite a useful little table.
Ooh, I've got my hand stuck. It's very small.
Legs sticking nicely? I wonder how strong it is.
I'll sit on it. I don't think I'm as heavy as you. Oh, thank you.
Who's going to sit on it?
You try sitting on it. If it breaks, it's your fault. You've got dents in it. Uncomfortable. And it's also dented. And the legs are going like that.
It holds your weight because of those tubular legs.
Pity those boys don't get to go. What's wrong? No.
Well, you've all been busy, haven't you?
Oh yeah. Can I have my one, please?
The square bridge is yours, Piers?
I'll just have to make mine's first.
Not a very strong shape, I'm afraid. Not much stronger than the cardboard you made it with.
Doesn't like it, does it? Look.
There, you've got a semicircular one. Oh, that's gone too. Tom, you've got a proper arch there.
Very hard to show.
Now I want to show you something. I'm switching to replay. For hundreds of years, people have known that one of the strongest shapes you can have is the arch. The Romans built this. And you can also make very strong things out of the weakest materials. Helicopter blades have to stand up to all kinds of stresses and strains, yet some of them are actually partly made out of a special kind of paper. The special paper is put into a mould and a sheet of carbon fibres placed on top. After it's been baked, the material is then strong enough for helicopter blades. Amazing, isn't it? Everybody here? Lear's scientific sweets have cooled down and they're ready.
Right, good luck to try some fudge.
Scientific toffee and a tray full of fudge.
I knew you would.
You know I'm the...
No peers, don't we? Here we are.
It's like glass. It's like a table. It's very like glass, doesn't it?
You're going to eat two materials made out of sugar. And they're quite different to each other.
Rock hard, as usual.
It's huge. Hold it up to the light. Sticky in the middle.
It feels.
Rather like a sheet of glass, isn't it?
Look.
You can see your hands. a toffee hand.
It makes it look.
Yes. Look at this.
Or something.
Look at the ends of this.
Yes, just like shattered glass.
I'm going to have another piece of that.
Oh, greedy guts, you're going to be sick if you eat too much.
No, I won't.
Let's have a look at that fudge. It's crystalline because the sugar was cooked slightly differently. No thanks, Tom. It would wreck my circuits. Never touch the stuff.
No.
Never touches it.
Can't understand what you all see in it, personally. Except, of course, it's quite an interesting material. But then, all materials are interesting, aren't they?